This topic discusses the neural network modeling method for the inline blending optimization for crude and fuel systems. This topic will discuss crude versus fuel products, blending and blending properties, and compare batch from tanks versus rundown blending directly from the process units. The blending problem is relevant for the refineries in two contexts. First, crude oil blending to get the crude for the crude unit, and second, product blending to obtain the final fuel products most cost effectively. Crude blending allows refineries to use opportunity crudes. These are cheap sources of crude oil, the properties of which are not admissible for the Crude Distillation Units, CDU, of the refinery. However, by mixing these crudes with others, the refinery CDU can process the resulting mix. Optimal recipes for mixing intermediate refinery products require consideration of multiple factors, considering the constraints on the properties of the blends and the capacity limitations of the refinery infrastructure. The high-level planning of the blends must consider the refinery's production capacity, the planned feedstock supply with final product distribution capabilities, and the planned production of various final products. In mixing the intermediate refining products, some dependencies between the properties of the blending components and their product are linear, while the rest are nonlinear. For example, the density and sulfur content exhibit linear dependency, while Reid vapor pressure, RVP, and boiling endpoint behave non-linearly. Therefore, an artificial neural network, ANN, serves as an effective tool to model the non-linear properties of the blend products. The predictive blend model based on ANN can solve the optimization problem for two principal gasoline blending cases. The first is mixing the intermediate distillation products stored in tanks. The other is directly mixing rundown streams from the refinery's process units. The second case is more challenging, as it requires handling more real-time adaptations, as the streams from the units may vary in time. Practically, we envisage three core steps. The blending optimization must consider the broad scope of the refinery's operations. At the highest levels, the refinery operations planning takes place, driven by the market demand for certain products and raw materials prices. These market constraints and the refining process model should dictate how many products the refinery should produce over a particular horizon of between 2 weeks and 4 months. We are considering allocating specific storage utilities and shipments to schedule at this stage. The next step matches the planned blends to the existing storage capacities and shipment schedule. Then, if the allocation succeeds, the offline recipes are produced. If the allocation of the available refinery storage facilities does not support the planned production, we must amend the plan. The offline recipe is a basis for real-time correction during the actual blend based on online analyzers' readings. The offline optimization spans a few blending periods and optimizes the recipes, considering more than one blending period. At the same time, the offline recipe does not consider the actual properties of the streams from the tanks with intermediate refinery products, while online blending works based on the stream properties measured in real time based on online analyzers' readings. So, in this sense, two recipes complement each other. The update of the offline recipe to obtain the online one happens concerning the cost function. The cost function penalizes the distance of the online recipe from the offline one, the costs of the components, and the deviation from the blend quality targets. Online blending is necessary, as no model can fully predict the properties of the intermediate product streams in advance, and specific real-time recipe correction will be necessary in all cases. The offline calculation may consider multiple blending periods. The online optimization searches for the locally optimal recipe in the vicinity of the recipe found by the offline optimization concerning the cost function. Complying with blend specifications may be a constraint for online optimization tasks. The offline optimization considers three groups of parameters: logistical constraints resulting from the scheduled arrival of raw materials and final products departure, constraints on throughput and storage capacity of the refinery, and the blend's recipe. The first step of the optimization is to define the recipe for the current stream properties measured by online analyzers. This recipe considers the deviation from the pre-calculated offline recipe, giveaway, and other factors defined by the cost function. The resulting stream will have a deviation from the predicted by the blending model properties. This gap must be closed intelligently, a function of multivariate feedback control. As the blend predictive model is trained on increasingly online analyzer readings for incoming and resulting streams, the gap in properties between the actual and the predicted blend streams is expected to diminish gradually. The deep reinforcement learning, or DRL technology, allows shifting the optimization calculation offline while pre-training a dedicated neural network to generate the set points for each blended stream control based on the current readings of the component stream properties and the blend task parameters. The DRL control policy adapts itself based on the gap between the blended stream's desired and measured properties. The DRL policy can be pre-trained using the digital twin of the blender. During the initial offline training, the output blend readings from the online analyzer are substituted by the digital twin predictions of the blend properties. The objective of the blending recipe is to ensure the blend's compliance with the quality specifications. If no real-time recipe adaptations occur, the variability of blend quality parameters requires taking a suboptimal giveaway, which requires using costly components in the blend. The ability to adapt the blend in real time, incorporating the more expensive components only when necessary, reduces the variability in the quality parameters of the blend. This reduced variability decreases the giveaway and over-quality incorporated into the original blend without increasing the danger of non-compliance with the quality standards of the blend. The summary. The research shows clear economic benefits of using blend optimization technology. We must note that the ability to adapt the recipe in real time depends on the storage tank's qualities and the blended product's final qualities. OMS eLearning Academy thanks ModCon for contributing this critical content about the process analyzers. We hope you have gained practical knowledge in this topic to help you understand process analyzers in the downstream refining industry.